Hello, everyone. I'm very happy to interview Professor Pinzul today. Professor Pinzul graduated from the Moscow Institute of Physics, where he also did his master's, and he earned his PhD from the University of Alabama in the United States. He's currently an associate professor at UNB and a member of the Relativity and Particle Physics group. So without further ado, I believe we can begin the questions. And I'd like to start by asking the main question of this interview, that being mathematical and theoretical physics. What is the difference between them? Could they be the same?
Ok. Boa tarde, bom pomeriggio, добрый день, good afternoon. Ok, isso 4 línguas mais ou menos que eu posso falar. Então, eu vou começar, na verdade, em português, explicando muito rápido porque eu estou falando em inglês, porque eu vou falar em inglês. Então, coisa, tipo, mais importante é o seguinte, que claramente eu posso falar em português, ok, pelo menos eu penso que eu posso falar em português, mas em inglês, apesar do meu sotaque bem forte, ainda o vocabulário é mais rico, então a conversa vai ser mais dinâmica, mais colorida, eu não sei. Então eu acho que eu poderia explicar coisas melhor em inglês, talvez. E segunda coisa, como já disse antes dessa entrevista, que todos vocês têm que culpar Alisson, porque ele sugeriu que, para mim, que eu falo em inglês. E eu só concordei, na verdade. Sim, eu só concordei. E terceira coisa, claramente, que, ok, isso tipo vai mostrar para todo mundo que nosso instituto tem essa componente internacional, sim, ok, então, muito bom. E mais um anúncio. Se nós temos agora alguns alunos da minha turma de Física Matemática, ou se eles vão assistir, porque isso vai ser gravado, então significa que esse anúncio vai ser oficial. Para mim, tanto faz como vocês vão fazer os seus problemas, ok? Eu preciso resposta correta. Isso não significa que só resposta vai dar. Eu tenho que ver como vocês chegaram nessa solução, ok? Então, porque várias perguntas, ok, você explicou como fazer isso assim, etc. Eu achei outro jeito, um outro jeito. Se seu jeito é correto, é correto. Ok. Inglês. So this question is actually very interesting in the following sense. I mean, it's very interesting as a question, but I mean, there is immediately when I saw this question, I recalled TOEFL. TOEFL, you know, this is test of English as a foreign language, which you have to take if you try to enter some American university, for example. In TOEFL, at least, I mean, like 30 years ago, it was a section when you had to write some short essay, like redação, on some topic. And there were some instructions, actually, how to write that essay, even if you don't know much about the topic. So essentially, in the first 2 lines, you have to take exactly that topic and just rephrase you in your own words. And then when you conclude, you should do the same. But I mean, now like some positive statement, but exactly just taking the topic and rephrase it. So the topic of my interview is exactly like theoretical mathematical physics, are they the same? So this question shows that whoever asked that question has a good chance to pass on TOEFL, because I mean, this question is exactly taking the topic and just, so are they the same? So the point is the following. The answer, of course, depends on who will be answering that question. So the best analogy means from my point of view. So whenever I say best or for sure and all this stuff, you should always understand this all the time from my point of view. So the best analogy is a rainbow, right? I mean, so it's visible part of the spectrum, which has this red, orange and all this stuff, and yellow, and ends with blue. So clearly, you can distinguish very clearly, like red from blue. But I mean, the transition, for example, from red to orange, it's actually up to you, right? I mean, so different person will tell, will point at different part of the spectrum and say, okay, so here it stopped being red and here it started being orange. Exactly the same thing. I mean, just imagine the spectrum, like experimental physics, applied / phenomenological physics, theoretical physics, mathematical physics, and then here's ultraviolet part of the spectrum which we don't see is mathematics, right? So most of the physicists, they really don't see that part. I mean, so theoretical and mathematical physics, they really near each other on that part of the spectrum. So which means that different people will tell, no, this is still like theoretical physics. Other people will say that this is mathematical physics. And confusion, there are two additional sources of the confusion, not confusion, but interpretation. That essentially theoretical mathematical physics, they concern with exactly the same questions. But methods of theoretical physics, they more rely like on physical side, let's say. And methods of mathematical physics, they stress on rigor. So meaning that they really try to analyze the same questions, but remaining as much as possible on the level of some well-established mathematical facts. So in theoretical physics, you can always hear something like, okay, so we describe in some physical model. So of course we assume that everything is fine, everything converges, blah blah, all this stuff, and typically that's what happens. So in mathematical physics, you don't do that. You prove that it really converges. What are conditions under which that physical system really makes sense? So that's more or less the idea. Additional source of the confusion is exactly that mathematical physics, just taken as mathematical physics, also understood differently depending who is asking that question. Because mathematical physics as an area is present in physics and in mathematics. Okay, so so meaning that in physics, let's say it's more like you are physicists which care about mathematical rigor, but still like you more or less want to explain physics. On mathematical side, you're a mathematician who is inspired by some physical problems, but after that he really treats that problem completely like mathematically, and even like developing already some things which already do not have direct relation to physics. So there are even two journals, Journal of Mathematical Physics and Communications in Mathematical Physics. So Journal of Mathematical Physics is published by American Physical Society. So it's more like physical. And Communications is published by Springer, I think, I don't remember. So, and it was organized by more mathematically inclined people. And if you compare the level of rigor on those in those two journals, you will clearly see the difference in the rigor. So the point is that depending on the point of view, they could be the same. So some people will will be looking at the same article, and different people would say that this is theoretical physics. Different people will say that mathematical physics. But clearly, there are some papers which will be like identified by whatever person is looking. Okay, so this is theoretical physics. This is mathematical physics. But there is very, very broad and vague transitional area. Okay, so that would be my long answer to the very complicated question.
Thank you for the answer, Professor. And the next question is, do you think mathematics was created or invented or discovered?
I remember that question. So my answer will be, so there are some questions further which are in some way related to this question. So I will answer in general by touching also the questions which will follow. Okay, so so when those questions will appear, I will say, I already answered that.
Okay.
So the point is that could you please allow me to share the screen on this second computer?
Yes.
Whoever, because I want to show something. Very nice. Okay. Application. Okay. Entire screen. Okay, so hopefully you will see something right now. Okay.
Yes.
So when I was more or less of your age, meaning like 30-something years ago, I was influenced very much by these two papers. So meaning that it wasn't an early influence. If you later ask me how I get into physics, I will gladly explain, but I wasn't like at 15 years old, I was publishing papers and all this stuff. I mean, so no, it was about your age when I was really struck by those two papers. I mean, so one by Dirac and another by Wigner, which essentially defined why I decided to go into mathematical physics. So they treat the same kind of questions. I mean, the importance of mathematics in physics with slightly different conclusions. I mean, so, but in particular, in the paper of Wigner, there is some partial answer to this question. So the point is the following. As you know, mathematics is kind of like axiomatic science, right? I mean, you have some set of axioms, and then you start playing with them. So those axioms, you can say that they were discovered because, I mean, they heavily based on our everyday experience. Like you really observe that if you have a line, you have a point, then I can draw another line which is parallel to that one. I mean, that is one of the axioms of Euclidean geometry, and so on and so forth. The same, like axioms of Peano of arithmetics. So those, of course, they were discovered, you can say. So meaning discovered through some generalization of our observations about the world which surrounds us. But as Wigner says, or observes, or comments, if you would just stay with those axioms, your game would be very short. Because, I mean, that's it, I mean. So what mathematician does, he says that, okay, so we have those axioms, let us put some additional structure. Like you have a set, let us call some sets to be special, open sets, closed sets. Some additional structure which is not directly related to our experience, everyday experience. So he adds some additional structure which is already dictated by something, by both Wigner and Dirac, they seems to be agreed that it typically is dictated by some beauty consideration. So it's a very nice construction. So let us study it. So that part of physics, of mathematics, of course, was invented. So meaning that you invent some additional structures which do not have typically immediate experimental or application or experimental representation in the world, and you start playing. But the rules of that game are very strict. you have to play with them only up to the point when it's consistent, logically consistent with the previous axioms, with the previous structures which introduced and all this stuff. I mean, so the answer is exactly like that. I mean, so I would say the mathematics started in some sense as an experimental science. So the basic axioms, they really rooted in our everyday world. But the future development, of course, does not have always a direct relation to our future world. That, of course, has many exclusions. I mean, so, for example, two completely like opposite or extreme examples: Riemann geometry and functional analysis. So Riemann geometry was discovered sometime in the middle of 19th century, just really like a logical possibility, no relation to physics and all this stuff. I mean, so very abstract science and all. Only like 60-something years later, Einstein showed us that actually it is directly related to our world. Functional analysis was developed as the reaction of mathematical society to discover of quantum mechanics. So functional analysis essentially did not exist before quantum mechanics. So functional analysis was stimulated by some experimental discoveries which led to quantum mechanics. So it was a reaction of mathematics, that mathematics felt very uncomfortable that it does not provide appropriate language to describe some physics and all this stuff. So about the language is a different story. So the main concern of Wigner, so by the title you can see that is unreasonable effectiveness of mathematics in the natural science. Like, why at all mathematics is the language for natural science? Actually, Gilfan is a great mathematician, Israel Gilfan. He commented on that paper that the only more unreasonable thing than unreasonable effectiveness of mathematical international science is a strange ineffectiveness of mathematics in biological sciences. So he was surprised that mathematics is not very effective in biology. So that changes actually. So short question, as I said, I mean, so the beginning of mathematics, they were discovered, but the whole beautiful building of mathematics, of course, was invented sometimes completely independent of physics or physical world, sometimes stimulated by the physical observations. But I mean, like pure math in general does not care about our world. So it's driven by pure beauty of the building. Okay, so that's the answer.
Very good. Such a classical question right there. Now moving on, but still a little on this topic, how would you characterize the relation between mathematics and physics? And can physics still be done without mathematics?
So that is really directed to this, directly related to this Wigner article. So relation is the following. So it seems universally accepted, and depending on the point of view, you either surprised by that or you take as a natural thing. So Dirac, in that paper, he was more inclined to think that is more natural. Wigner was, that mathematics is the language of physics. Wigner was, through all those 14 pages of his article, constantly surprised that this is true. So the point is the following, the answer to the last part of the question, because mathematics not just is a language of mathematics of physics, is the language. So Wigner makes that very much clear in the following sense that, I mean, so of course, I mean, like in my case, okay, so I speak several languages, but only in Russian, I'm really native speaker. So only in Russian language, speaking Russian, I will be really freely expressing myself, not thinking. I mean, you always should think what you say, but I mean, in a different way. I mean, so not thinking how to say that. I mean, so if I have idea, I can express it. In English, it works close to that, but not ideally. In Portuguese, it's even further from that. In Italian, it's on rudimental level. I mean, I can say that, like, thank you, give me your money. That's it. I mean, but the point is that, so mathematics is the language of physics. So meaning that it's the most natural, appears to be the most natural. So Wigner was surprised, not just like why mathematics, why we can use mathematics to calculate something. The first surprise should come actually why we can use mathematics to express the physical laws, not to calculate, but really write the physical law in terms of a formula. But I mean, if you think of that, you should take one step even before that. So the first surprise actually comes why the nature at all has physical laws. And those physical laws, they could be very restricted. So for example, you can have like a law of like gravitation, which is applied only to gravitation, independently of the fact that a lot of stuff around happening, all the stuff, but still with very huge precision, enormous precision, you can really idealize gravitation and just use that law to describe just that. So you should be very surprised by the very possibility of idealized description of our world. So after those two papers, I actually came up with my own recipe. So I'm more on the side of Dirac than of Wigner. So I'm not that surprised in some sense. I mean, so actually that relates to the previous question. I mean, so because mathematics is intrinsically based on some experimental facts, axioms, and then every logical possibility in some sense, which is consistent with those facts, is developed. And because our universe is effectively infinite, every logical possibility should be realized, or in principle. So because that's why every mathematics, independently how abstract it is, should find sooner or later some physical application. In some sense, that was a recipe of Dirac, how to discover new theories. He said that essentially, like, take some mathematical branch of mathematics, some area which has not been applied yet to physics. Study it to the very deep level in such a way that you will be really like understanding it very well, and then think which physics could be explained by that mathematics, because he believed in this beauty that mathematical theories should not be wasted. If there is some mathematical theory, sooner or later, in some sense, it will be applied to physics. It might be very unexpected. It does not mean that it's necessarily some fundamental physics. It could be some very specific effects, for example, and all this stuff. So I do believe that at least I don't see how we can describe our world without relying on mathematics as the only and the natural language. That's the answer.
Thank you for the answer, Professor. The next question is, what are the main problems in theoretical physics nowadays, and how are they related to mathematical physics?
So on Wikipedia, if you just type like unsolved physical problem, there is a beautiful article, meaning that really listing all the problems, physical problems, categorizing them and all this stuff. I mean, so really nice. I mean, I can give you the link after that. I mean, so meaning that I think that article will give the best answers. So you can just browse through that article and look what topic you like to enter. So of course, I mean, I have my favorite ones. I mean, so meaning that the favorite ones which stimulate my research. On the top of the list, of course, I mean, this problem of quantum gravity. Right, I mean, so because I mean, there are like two most well-established theories which pretend to be like almost fundamental. It's quantum physics and general relativity, which do not like each other. Yet there is a strong belief that they have to marry sooner or later. They should become a unified theory one way or another. So that's the problem of quantum gravity. Actually, a lot of fundamental problems to be believed will be solved if we have this fundamental theory of quantum gravity. I mean, there is no guarantee that this is true, but I mean, clearly having more general theory, which will unify whatever we know, will help a lot. So in particular, it might automatically solve those problems of unsolved on that list. Dark energy, dark matter, those problems might obtain automatically solution. The problem of confinement, which is also on the list, right? I mean, so we still do not have a clear understanding why in quantum chromodynamics we have a confinement of a color, meaning that why quarks, they don't fly around us. Why we have only protons, neutrons, which are really bounded states of quarks. I mean, so essentially, whoever will manage to calculate that explicitly, like essentially, like to calculate the mass of the proton, knowing the masses of quarks, for example. So if you want a Nobel Prize, okay, so go ahead, calculate that. I mean, so that is automatic Nobel Prize. I mean. So the list of unsolved problems is very huge. It involves like the problem related to some turbulence, like Navier-Stokes equation, the study of the. So many problems. So my problems, my favorite, as I said, related to the quantum gravity taken in a very broad sense. Okay, so what is that? Is it really some valid question? Maybe, I mean, once again, if you look at the Wigner paper, there is still, strictly speaking, no guarantee that we will have any unified theory. So nobody said that the world, that the nature is so nice as to give us possibility really to describe everything by some grand unified theory. So maybe the nature is just like that. It will be like described by patches of different physical laws. That law is applied for that, that law applies for that. I mean, so our belief in grand unified theory, whatever it is just based on our current experience. That, I mean, so far it worked in some unifying way. Nobody said that it will keep on going like that. Okay, so that's it.
All right. So now for a bit of controversy, which approaches to solving these problems do you think are still valid and which are not?
So in some sense, one of the approaches I already cited, as I said, I mean, so that's exactly the paper by Dirac, right? I mean, just study math. So that's approach, like from my side as a mathematical physicist. Try to find math which you think is very cool, very beautiful, very like advanced, but yet has not found its application in physics. And just really try to see whether that math will fit some physical phenomenon, not necessarily once again fundamental or not. So in some sense, this is a very safe approach. Even so, after you study this very, very cool mathematics, even if you will not succeed in applying it to some physical phenomenon, still you'll be feeling very cool, because I mean, for sure, almost nobody will know that math. I mean, and you will be feeling like very superior to your friends. I mean, that okay, so you don't know that, and I am very, very cool person because I can easily like tell you what is that. I mean, so meaning that, but first and most important, that it should be fun. I mean that you really should enjoy. Should be enjoying that. I mean, so meaning that you never can really set a problem that okay, I have to solve that problem, whatever it takes. Yeah, you should really enjoy the process. Okay, so so on the serious side, as I said, I mean, so because I do believe that mathematics is the correct language of physics, as usual, to better express yourself, so meaning that in this particular case, to better explain physics, you have learn better on more deep level the language, mathematics. Okay, so, and of course, I mean, it does not mean that you don't have to learn physics, because I mean, you always hear that like big discoveries, they happen on some borders of different sciences or different areas and all that stuff. So of course, I mean, more you know about physics, about the physics itself, better chances you have to succeed. So for example, I mean, a lot of techniques in quantum field theory, they came from condensed matter. So now imagine that you don't know condensed matter and just working in quantum field theory. Then you actually have much less chances to succeed compared to a person who actually studied very well condensed matter. Vice versa, in condensed matter, there are a lot of applications of quantum field theoretical methods. So if you just learn very well those two areas, you already have much better chances to come up with some new theory or new solution to some long-standing problem. So essentially, the recipe is very simple. I mean, there are two answers. The first answer, or you have to be born a genius, then you don't care about anything what I said. You're just genius by definition, and you just have some insight and explain. Still, you have to learn stuff. Or you don't take your chances and don't believe that you're a genius, then you study a lot. And you study a lot, not just your particular very narrow area, but you study a lot, really a lot. And you try to make your study as broad as possible. Okay? So those, I think, the only valid approach, because otherwise you're doomed. Okay?
Okay, thank you again for the great answer. And the next question is in the same topic. It's about, there has been a lot of talk about the need for a new math to solve these hard questions. How would this new math look like? Mm-hmm. From what areas of modern mathematics is it more likely to arise from?
Okay, so if I would know how this new math would look like, I would be probably much more famous. Okay, so the main point that this new math might not exist yet. The standard example is exactly as I told you earlier, is quantum mechanics. Okay, so quantum mechanics was discovered without having the correct mathematical theory. So the mathematical theory appeared just several years later, and it was developed essentially by von Neumann, right? So von Neumann started creating functional analysis. I mean, of course, a lot of like preliminary work was done by Hilbert, other people, Banach, stuff. But von Neumann really made it into science, into the area, which more or less we call like functional analysis, so theory, operator theory, and all stuff. So meaning that, of course, in some sense, they were in much better position than we are right now. Meaning that they really had very strong experimental evidences that we need some new physics. So right now, even the fact that we have like this dark matter, dark energy problem, it's not a strong indication about really new physics in the form of new theory. Meaning that you can incorporate all those things into some extensions of standard cosmology, standard model, and all this stuff. So without really using some very highly innovative and new ideas. So in the age of quantum mechanics, it was really a serious problem, a contradiction between the atomic spectra and classical mechanics. So meaning that you could not really make peace between those two, because classical mechanics combined with classical electrodynamics predicted that the spectrum of atoms should be continuous, and the observation was showing that the spectrum of atoms was discrete. So new physics was really required. And after it was discovered, now we can give arguments that we can like almost like derive quantum mechanics in some sense. But of course, at that point, it was very much like guessed by using some ideas of de Broglie on one side and Heisenberg on another side, and then it became quantum mechanics. But it appeared as two different quantum mechanics, right? Matrix and wave quantum mechanics. And only after that, the appropriate mathematical apparatus was developed. So without strong motivation from the physical side, functional analysis, sooner or later it would have been developed, because it started being developed once again before that, but it would take much longer time. From the modern mathematics, which already exists, I would say that exactly this part of mathematics, functional analysis, quantum groups, it's a different part. So quantum groups, it's some deformation of the notion of the usual Lie group. They're very important. So functional analysis is very important because it enters the very core of the formulation of quantum field theory, local quantum field theory, exactly from the mathematical point of view, in the set of axioms. So that's the language of the local quantum physics, functional analysis. Quantum groups are very important because they are natural, more or less natural, deformations of what we call symmetries. Okay, so symmetries. So we do believe after Wigner and Dirac, so Wigner got his Nobel Prize essentially for heavily using symmetries in this in his study of physical theories. So Dirac considered symmetries as the part of his definition of mathematical beauty in physics. So, but nobody said that the symmetries should survive in our classical sense, like Lie group Lie groups and all this, or some other type of algebraic objects should survive all the way to whatever energy scale and stuff. So we already observed the deformation of the notion of the symmetry, right? I mean, in the time of Newton, classical mechanics was based completely on the symmetry, which is just Galileo symmetry, right? I mean, which is given by some group, Lie group. But then we learned that it's actually Poincare group, which is actual symmetry group. And we learned that the previous symmetry Galileo group, in some sense, is a very singular limit of that one. So I mean that we passed from one symmetry to another one, still remaining in the same area of Lie symmetries, but the symmetry actually was modified. So who said that we always will remain with the same notion of the symmetry? Maybe the notion of the symmetry will be deformed. So quantum groups give you some hint along which lines that notion could be deformed. But I mean, once again, different people will tell you different favorite areas of mathematics. I mean, so, but my personal belief, once again, that there is a very, very good chance that the correct mathematics has not been invented yet. I mean, so that's related to the question: discovered, invented. I mean, so really invented. I mean, so because we have really serious problems with the experiment, so meaning that very difficult to expect that we will have some breakthrough experiment of the level which will really confront heavily our existing theories, because it will require higher and higher energies. So there is much better chance that the discovery will happen along some lines of logical possibilities, consistencies, beauty, and all this stuff. Okay?
All right. So we're going to move on to the questions on the chat now. A lot of questions.
I can see from the chat that not my, so people probably are waiting for this video to be legendato. Right.
Oh, it will be. It will be. In the future, it will be. We guarantee that. Still, there are a lot of questions. So starting here with Lorena. So going back to the second question, she asks, so basically we can understand mathematics as a science both created and invented?
Right. I mean, so I would say, well, once again, that the beginning of mathematics was, I mean, no, let me step back. What is the difference between created or invented? So, meaning that I would say that the main building, the building of mathematics was created and invented, meaning that in the following sense that the basement or the base of the building was discovered in the form of the axioms, but every next level was essentially created by mathematicians, and that process of creation was, once again, sometimes purely driven by the imagination of a mathematical community. Sometimes it was stimulated by physics, by the natural world. Okay, so but I mean the base the base was clearly I mean, for me, clearly discovered. That is why I do believe that the mathematics is the natural language to describe the world, because mathematics in some sense has as a foundation really some experimental facts absorbed by us, by people. Because I mean, you should never forget that when we describe our world, we describe this world as macroscopical people. So that is the main problem with the interpretation of quantum mechanics, because we, as some macroscopical objects, trying to understand something which is beyond our scale, well beyond our scale, which is microscopic scale. So essentially, we try to translate. So microscopic scale might have its own language. So what we're trying to do, we're trying to translate the language of the microscopic scale to our language. So our mathematics, in some sense, by definition, intrinsically macroscopic, even though it could be addressing some questions which are differ by scale in every direction, in many orders. Still, we try to translate it one way or another to our own language, created by us as macroscopic people. Okay, so that's why the problem is interpretation of quantum mechanics, because I mean, we're trying to adopt something. Look what we do. We have the whole quantum mechanics, the usual one, non-relativistic quantum mechanics. We still keep on using some macroscopic things, momentum and coordinate, because we cannot think other way. So the problem, of course, I mean that very much probably that for that scale, for the atomic scale, of course, those notions are not very much relevant. But we cannot just come up with some other concepts, because I mean we don't have those concepts. Okay, so once again, the foundation of the building by the name mathematics was discovered. Every new level was created and invented. Invented meaning the following exactly. So okay, so now I have difference between created and invented. So invention is the first step. When you have something and then you say, okay, let us add some additional structure. So that's the moment of invention. And then after you added this new structure, you start developing the consequences. So that's the process of creation. Yay. Okay. For some reason, I don't hear. I lost the.
Yeah. Oh, I think
all right.
Okay, I'm good. Thank you for the answer again. And the next one is from Lorena, and she says, as a mathematical physicist, what do you see as more important in writing a well-structured theory? Its mathematical background or its physical phenomena, or both?
So
a big one.
Right. No. So I used to say to my students, I mean, a little bit jokingly, but I mean, in some sense, I'm completely stand by that point. I mean, so why I do mathematical physics? I think that mathematical physics is much safer than applied or experimental physics. In mathematical physics, at some point, you could stop caring about the actual world, and you play with so-called toy models inspired by physics, but you don't care really about the actual numbers. Like you don't care really to derive that particular cross section or that decay rate and all this stuff. I mean, so for me, it's really like that. I mean, so physical phenomena serves as some motivation, very strong one. Then you try to come up with some mathematical model which will try to touch at least some aspects of that physical phenomenon. I mean, you cannot hope to be so lucky that, like in one step, you will just describe the whole phenomenon. Like in the case of the Einstein, and even in the case of the Einstein, it wasn't just one step. I mean, it took really like 10 years to get to the point, right? I mean, so I mean, when he created general relativity. So I would say that the relation in the theory from the mathematical physicist point of view, physics serves as a like enormous supply of ideas for models. But after you pick your model, then at least for some time, you don't care that much about the actual physics from the point of view of applications. First, you try to really develop your theory in such a way that you are happy. Mean that you really feel that theory is very consistent, pretty. It uses some very nice connections, unexpected, from which you can see that, oh, this is nice. So this structure really naturally falls into the picture and all. So when the theory matures and it reaches the point when it starts looking more and more as a physical theory, that's the moment when this theory starts slowly moving from the side of mathematical physics into the direction of theoretical physics. Then from theoretical physics already it will connect with experimental physics, applied physics, and all this stuff. And so for me, mostly if you look at my papers, just several of them have actual numbers. And mostly because, I mean, if I would not put those numbers in the paper, probably it would not have been published. I mean, so mostly I'm playing with some, which is a very popular name, like toy model. Okay, so model, mathematical model, which you use to test some ideas which potentially might be applied to some physics. Okay.
Okay.
All right.
I don't know whether Lorena is happy or not. I mean, but that's my point of view.
All right. Now for the next question, you already talked a little about this, but if you want to talk a little bit more, someone is asking, what math does theoretical physics use?
Okay, so I can just really list it. I mean, so the analysis was essentially invented by Leibniz and Newton to describe more or less what we call classical mechanics. Right? I mean, so to some extent, of course, I mean, it's very useful also in classical field theory, like not to some extent. It's useful to describe like electromagnetism and all this stuff. But in electromagnetism, you already know that a lot of things more naturally described if you use the notions of differential geometry. So analysis, then all different aspects of geometry, starting with topology, differential geometry, Riemann geometry. So Riemann geometry, this is already general relativity. In between them, very important stuff, as I already tried to stress several times, let's say algebra in the form of group theory and all stuff, because that's the part which controls the symmetries of our world, and that part which enters all possible areas of physics. Okay, so you have symmetries in almost any area of physics, and not just physics, biology, and all stuff. And so analysis, algebra, essentially in the in the form of group theory, it's universally applied. Geometry, it's more already tending towards like theoretical physics, like quantum field theory and general relativity. Then, of course, complex analysis. So complex analysis is very, very important tool, and not just a tool like which helps to simplify things. A lot of things cannot be really even appropriately reasoned without complex analysis. Like in quantum mechanics, you know that the Hilbert space is over complex numbers, not over real numbers. So I mean, complex numbers somehow, so complex numbers is an example of some abstraction which is not experimentally like necessary originally, was invented, and that happened to be very important in physics. So I have my point of view why important, but that's different story. Then lately, after quantum mechanics, what I said, very important functional analysis, of course, operator theory. Since 60s, operator theory, functional analysis became heavily important for the study of axiomatic quantum field theory. So meaning that if you really want to understand quantum field theory, really not in applied sense, but really like on the fundamental level, like why it is there, I mean, then functional analysis is your friend in the form of C-star algebras, von Neumann algebras, so functional analysis. So I would say that those are the main areas which you have to learn. So geometry in all the manifestations, analysis in all the manifestations, meaning that the classical analysis and functional analysis, and algebra, like algebra, thinking about symmetries, group theory and all that stuff. Those three things you cannot avoid if you want to do not just mathematical physics, but theoretical physics. If you want to do theoretical physics, probably you don't have to learn that like with all the proofs of the theorems and all this stuff. I mean, so it's enough really to have a solid form control. If you want to do mathematical physics, you will be impressed how some fine points really on the level of some theorems, conditions of theorems, which you typically say, so that is assumed. So, and that which is assumed can change the game completely. Okay, so for mathematical physics, you have to really become quite strong applied mathematician. Okay, why applied? Because once again, I mean, it's very difficult to become a mathematician, pure mathematician, if you haven't been trained from your childhood to be a mathematician. I mean, so if you are trained physicist, you will remain a physicist with a chance to become a good applied mathematician. Okay, so that's the answer. I think that's the answer. Okay.
Well, the next question is from David, and he says, as a mathematical physicist, how much do you need to keep up with the new mathematical developments?
So I think like for the past 58 minutes and 26 seconds, I try to like persuade you that you have to, meaning the following, that I think that's one of the biggest chances for us to make some breakthrough, to apply some new mathematics. Okay, so once again, there is a chance that actually the new mathematics will appear as the reaction to some new physics. But at the moment, I would say the chances are better that some new mathematics will be realized, that some new mathematics is relevant to some physics. So this means, of course, vice versa. This does not mean that you really have to study every new development in math which just appeared in the stuff. I mean, so I would say that you should be aware of new directions in math which have been more or less established, meaning that it's not like really like new idea and just like two mathematicians really care about that. I mean, so probably that's not the thing, correct thing to do. I mean, so but if you see that there is some emerging direction in mathematics, some new one, then probably you would like to see what is that about. I mean, at least, I mean, like to see some lecture or some seminar, really like for non-specialists, really to understand, I mean, what is going on in such a way that in your head, you will have some check mark. Okay, so that mathematics exists. And when you, at some point, when you like have better control of the situation or learn some new physics, it might click that, so there is mathematics which might be actually very useful for that. I mean, and then at that moment, of course, you enter and you have to do your study, your homework to study that area, to see what is the development. But once again, that is better to do because we are not trained mathematicians. The best way to do, actually, to find some mathematician which will help you, which will direct you through that area, meaning that you will not just be wandering blind in that area, just like rediscovering by yourself. For that, we have actual mathematicians. I mean, so they could say, okay, so what is known is better summarized in that review article and all this stuff. So I can answer your questions and all this stuff. And so the best way is actually to have your own Marcel Grossman, right? I mean, like in the case of the Einstein. I mean, so that would be the best way. I mean, the best way to be an Einstein, first of all. So, but then even if you're Einstein, it's very cool to have your own Marcel Grossman, which will tell you, okay, so the math is like that. I will explain it to you. Okay.
Find a mathematician to call your own, something like that.
I mean, he's one of the best friends from from the first year of the university. So he was his own Marcel Grossman, right?
Yeah.
Fair enough.
So everyone needs to make friends.
I mean,
with
Marcel Grossman could have said that I have my own Einstein. I think.
Yeah. It's a mutual friendship.
Right.
Everyone wins. All right. So moving on to the next question now. Someone is asking, what are some of your advices to a young physicist who is just starting his career on mathematical physics?
So before I started this interview, one of my students, former students, she wrote to me nice, like this interview and all this stuff, but try not to scare students from mathematical physics. I said, why? I said, why? If they like too easily scared, maybe they should not be in mathematical physics. Okay, so advices. The universal advice, of course, is to study a lot. The study should not be chaotic. So meaning that you should not just like take that. I mean, so it's like the study should be organized, meaning that you should have a plan. So the best way to develop a plan, of course, to have some older friend, older not by age, by the qualification. I mean, ideally a supervisor, right? Which will more or less tell you what you have to study. You could discuss more or less like time frame, because I mean you might think that, okay, so if I will study that in 1 year, this is good. I mean, so it could be that time could be unreasonable in both directions. I mean, so I would say that no. I mean, 2 months, because if it takes 1 year, so then probably you should really think. I mean, you're really choosing the career for the rest of your life. So it's better actually really to test whether you like this career. So if it takes like too long and it's too painful, it does not mean that you're stupid. It just can easily mean that it's not your thing. So try some other stuff. I mean, so if after trying some other stuff, you would decide that no, still, I mean, though it was painful, but I like it. Okay, so come back. So the point, but it could be also unreasonable this 1 year in other direction. They say, no, I mean, this is impossible to learn in 1 year. I mean, if you do that in 2 years, you already can consider yourself like a very successful student with good chances to succeed in mathematical physics. So very important to have some qualified friend or supervisor which will guide you. Okay, so but what is much more important is that independently of whether it's hard for you, whether it's difficult or not, you should be having constant fun. Not in American sense, like, I mean, the school should be fun, let's play. No, fun meaning that you really should enjoy what you're doing. You really should enjoy learning some very, very heavy abstract stuff, and you should enjoy it not only by like reaching the point, I mean, like finally learning that, but by the process. I mean, so fun does not mean that it's easy. If it's easy, it means that you're doing something wrong. Either you learn it superficially, or you learn this stuff in like very slow rate, so that's why it's easy. I mean, you should really constantly feel challenge, and that challenge should be really enjoyable for you. If it's not fun, it's almost 100% indication that you should try doing something else. There is no shame in that. I mean, so I mean, there are very small group of mathematical physicists, theoretical physics, and they're not smarter than other people or stupider. They just doing what they like. Okay, so that's the main advice. Make sure that you really like it. Okay, so later I might show you. Some of you actually might have seen it. So some time ago I was asked, I don't know what's the reason, like to give some speech to Caloros. That was a stupid idea, but I mean I gave that speech. I mean, so and essentially the whole speech was about that. You might really reconsider your decision to enter physics. Like quit it till it's too late. I mean, so it was some like block scheme with a lot of questions, yeah or no, and answers like yes or no.
Are you sure you want to do this?
Right. I mean, so I don't know. I was told after that for some reason students liked it. I mean. But in any case, I mean, so advice for the person who decides to enter mathematical physics, make sure that you like both sides, that you like physics and mathematics. So that's the first thing. Then spend some time, let's say several months, of really active work, meaning studying something which you have never studied. I mean, and that's something like recommended by you, by someone. Like try to do that. I mean, and then after those several months, like check your feelings. Are you still like really up to going into mathematical physics or no? If you're really still up to, then keep on hard working. Okay, studying more. Mathematical physics is very difficult in the following sense. Difficult and different in the following sense. So that's the main difference, I would say. That you should not expect any quick result. So in some applied physics, in experimental physics, after 1 month, you will be feeling like already working. You will be standing in front of some device, and you will be really feeling like you're involved. In mathematical physics, it will take some quite long period of time before you actually will start understanding problems. So for me, that's the main difficulty. For me, it's very difficult to give some original problem to some younger person. I mean, I can give, of course, but I mean, that person will just not understand even what is the problem. Okay, so you should be ready to some long period of time when mostly you will be working very, very hard without any explicit reward in the form of some publication, all this stuff. I mean, but if you do work, sooner or later, it will be there. So I mean, I do have master students with publications, of course. I mean, let's say 50-50. 50% of my master students, they defend masters with paper, with a paper, at least one, 50% without paper. And it does not mean that that other 50 is like less qualified or stupider or whatever. No, they just were given the problem, for example, that did not have like this direct way to solve it. I mean, it just means that I did not know how to solve that problem quickly enough. Okay, so so that's the main like heads up. Be prepared for a long period of hard working without an immediate result and immediate involvement in the actual research. Okay, so that's why it's very important to have during the like first year at least this periodic check. Okay, so I still want to do it. Okay, so keep on doing. I still want to do it. I mean, because I mean, sooner you will understand that it might be not for you, really better for the rest of your life. And once again, you never should think of that if you like you should not even use the word fail, but if you did not like it at the end, in some sense it's problem of mathematical physics. So mathematical physics is some area that you did not like. Okay, so I don't like rap. Okay, but still it exists successfully. I don't like the fact that rap as a music exists. I mean, but I mean, still it exists independently whether I like it or not. I mean, so the same with mathematical physics. I mean, you can happily exist separately. But I promise that if you really will keep on doing it, I mean, then and enjoying it, I mean, then you really will have a lot of fun with mathematical physics. Okay.
The next question is, do you believe that we will be able to solve the problem of quantum gravity as soon as possible? What's the state of art in this field?
Okay, so some people, by some people, I call people from string theory, they claim that they already solved it. Some people from loop quantum gravity, they might say that, okay, so we like kind of solved it. I mean, so yet the rest of the community thinks that, of course, I mean, there is still no solution to quantum gravity in the physical sense, meaning that we still don't have a consistent theory of quantum gravity in such a way that potentially can give some predictions. Maybe those predictions even not are possible to measure right now, but really definite predictions. For example, like in the case of the string theory, the prediction should be that we should be able really, in some sense, to derive low energy limit in the form of the standard model. Of course, I mean, they don't have it. I mean, there are reasons for that. In loop quantum gravity, some other problems, like they have understanding more or less what is quantum gravity. I mean, less quantum space-time, but they have problem recovering, let's say, our usual commutative space-time. So the point is that the problem, from my point of view, of course, has not been solved. Do we have a chance to solve it soon? I mean, it would be fun, for sure. It's very difficult to say. So meaning that the situation right now, in the lack of strong experimental evidences in which direction we should move to find this new theory. So I would say that the better chances that for sure Lorena, if she enters this area, will have good chances to become a mature mathematical physicist, and yet to have her own shot at the problem of quantum gravity. That meaning that the problem quantum gravity will not be solved by the time Lorena will become a scientist. But of course, I mean, there is always a chance, let's say, of Einstein, right? I mean, this factor of Einstein, that all of a sudden somebody will come, the person which will see it through, and just will really discover it from his own personal reasoning, which will take some time for the rest of the world really to appreciate, as in the case of the general relativity. But then after that, everybody will be saying that probably this is the most beautiful theory of all times. Like still, like general relativity is considered like the most beautiful theory, right? I mean, so there is always the chance of that such person. So to answer really to Lorena, so Lorena, you could be that person. Okay, so I do think that we still don't understand, I would say, which the correct path and what is the correct mathematics to solve the problem of quantum gravity. In some sense, there are a lot of people which do think, as I said at the very beginning, that maybe there is no problem of quantum gravity. I mean, really in the sense of quantum gravity, really in the sense of joining of like gravity with quantum physics. Maybe there is something completely different. Okay, so I would not expect the problem to be solved tomorrow. Okay.
Very good. Thank you, Professor. We have a personal question now. Someone is asking, why did you decide to study physics?
How much personal?
It's about your career, your life decisions.
Your reason to study physics, basically.
Yeah, so why did you decide to study physics? Did you face many challenges as a researcher?
Okay. So can I share the screen again? I mean, that's kind of the question which you expect during the interview. So I prepared meaning that I had some slides prepared for completely different thing. So I adopted those slides exactly to answer this question.
All right, let's see.
Let's see if I manage share screen. And what do I want to share? Okay, so I want to share this your entire screen, right? Okay, so the story of my life. So, I mean, pretty much should be clear at what city I was born. So I was born in Moscow. So that's my path to physics. So at this age, I had no interest in physics whatsoever. Okay, so at this age, I could already read, count a little bit, but still pretty much not in the sense of like that I really thought about physics or something like that. I mean, so at this age, I think, so it's like 6-year-old or something like that. I mean, so I think that was the first hint that might be that I will like actually not physics actually. So that hint was, I mean, I should taken that hint that I should become a mathematician. That was a hint that maybe I should like mathematics, because I remember actually that time. So once again, it's like 6-year-old, slightly before school. So I was enjoying a lot of like doing some arithmetic examples, like 3 plus 5, 15 plus, even with some 2 digits and all this stuff. And I was constantly bothering my dad, like, okay, give me the next example, give me the next example, give me the next example. And he was so tired that at some point he said that, okay, 5 plus x equals 8. And that's it. I mean, so I shut up like for several hours. So then I just came to him and said that, okay, so if x is 3, then I understand. So that was when I learned how to solve linear equations. Okay, so so meaning that so since then, more or less, I got interested in, let's say, not in science, because I did not think, of course, in these terms. But I mean, that's why I eventually entered the like specialized the later school. Like last 2 years, I entered this school of physics and mathematics. So as you can see, I'm trying to explain the molecular the kinetic theory of ideal gas there. So this is like I'm 16 or something like that. I mean, 15 probably. So that's school. I mean, so by the name of the school, it means that I already was really very much interested in physics and mathematics. But because it was like still Soviet Union, so people were much more idealistic. And I was like still dreaming like going to space, even when I was 16 or 17 after that, I mean. So, and we had a very special university, which was specialized in preparing like engineers for space program. So I decided, okay, so I want to go to space. I like science, so I will go to that university. So that's how I entered this university in Moscow. This Moscow University, Moscow Technical University, or something like that. I mean, so they really specialized in training specialists for space program. After 1 year at that university, I understood that my point of view about what is to become a specialist for space program was heavily distorted by some romantic books and all this stuff about space travel. So in reality, that 1 year was heavily packed with technical drawing. We had 3 courses on technical drawing, of different courses on technical drawing, some specialized courses on properties of materials and all this stuff. I mean, and that was just like first year. So
you mean like
I decided,
machines and things like that?
Right. And so so I mean that it was technical drawing, really like drawing some schemes. Then it was projective geometry, but in the sense of drawing, really how to recover, how to draw 3-dimensional projective images of some stuff, and how to recover
geometry. Yeah.
Right. I mean, and then it was technical drawing in the sense that they would really put some stuff, some geometrical figure, put some lamp. It will be some shadow, and you really have to draw it. So it's 3 courses.
Wow.
I mean. So from the last course, I still have something remained in me. I might show it later. But the point is that I hated it. I mean, so I said that like screw space travels. That's not really what I want to do, and I quit that university. So because I quit the university, it means that I lost my protection from military service. So which means that for 2 years, I entered the army. So when you, for 2 years, like doing military service, you don't care very much about physics, mathematics, or whatever else. I mean, so essentially you want to sleep and eat. So very basic instincts.
Were you doing some technical work in the army? Or is it just...
No, it was, I was really serving in Moscow as a firefighter for 2 years.
Wow.
So, because in Moscow, I mean, this this firefighter service, it really belongs to military, because I mean it's a lot of very important objects and all this stuff. I mean, so meaning that a lot of work. I mean, so during some days we had several fires. So I mean that you really just don't have time to return. I mean, so you're coming back to your place, and while you're coming back, you receive some new call, and you just do U-turn and go to some new fire and all this stuff. So clearly no physics. I mean, closer to the end, or I had some slightly more free time, so I managed to prepare to enter another university. So, and after 2 years, I actually like stopped being a firefighter. I entered another university. No, so before that, so that's my hobbies. So you would not think that I'm like some geek. I mean, I am probably a geek, but I mean, not just about physics and mathematics. I mean, so that's I like to do. I mean that. So who knows me probably already know about me, that for me it's important that I like to do that. I don't care that much whether other people like it. I mean, so if they don't, I mean, they just don't listen. Okay, so but I like to do it a lot. I mean. So the second hobby, of course, I mean, I like to read a lot. So from my space program training, I like a lot to read some sci-fi. So that, but I mean, of course, in classical literature too. I mean. So that's from technical drawing. What remained from technical drawing. So from time to time, very rarely, I like to draw. So mostly I draw when I have really nothing to do else and I cannot play guitar. I mean, so that happens during the conferences, right? I mean, so because you're sitting, you listen some seminar.
Yeah.
That would be very inappropriate, like just to start playing guitar. So I draw. So that set of pictures from one of the conferences. I mean, so as you can tell, that was conferences on some. So the first picture is about the. So there was some talk on string theory. So that's actually the amplitude, some string amplitude. Okay, and inside that amplitude is the string itself. I mean, so that talk was talk about the massive neutrinos. That talk was on the symmetry breaking, and that was my general impression of the conference program.
Great.
Okay, so after army, after military service, I entered this university, which really specifically trained physicists. So that's I don't know whether you see it, that's exactly the T-shirt.
Oh.
So you can compare.
Moscow Institute of Physics.
Yeah.
And Technology.
Right. So that's so by the name, it's really just the whole institute is a very compact institute, but it really prepares only physicists for different areas of physics and all this stuff. I mean, so my area was I was at the department of essentially like theoretical physics. So that's why I was trained as a physicist with very strong. So meaning that really great place. I mean, so it was,
weren't you interested in plasma physics due to your interest in space technology?
So about plasma physics, let's say like that. I mean, so independently whether I was interested or not, I was forced to take the course.
Oh, okay.
So after which I understood that I have no interest in plasma physics because it was so heavy. Meaning that it's so heavily nonlinear with all those nonlinear equations and all this stuff. I mean, so I decided that I want something simpler. So that's why I entered mathematics. So
simpler, right?
Simpler than plasma physics. So I prefer.
No, the point is that in plasma physics. Why I'm thinking that plasma physics is more complicated than mathematics, because in such an area you have to keep in your head much more information, which you cannot logically derive from some previous facts.
Yeah.
So I mean that you really have to keep in mind a lot of some experimental data if you want to be effective. Okay, so in math, in principle, because it's in some sense more logical, so when you start seeing the whole picture, for you it's much easier actually like to orient in the area of mathematics and all this stuff, because I mean for you it's I mean, of course, I mean whoever does plasma physics will say that I'm completely wrong, but that was my impression. Okay, so that that in areas like plasma physics or whatever actually applied area, you actually have to know much more in the sense of knowing a lot of facts. Really, like not really like some logical path or whatever, or some, but really facts. I mean, and sometimes that fact is just a fact, experimental fact. Okay, so and only when you like know a lot of facts, okay, now you start seeing the pattern, and you trying to explain that pattern and all this stuff. I mean, so for me it was very difficult. I mean, but I had to take it. I mean, so that was the point of education. I mean, so I had to take almost any possible physics to make an educated choice of what I like. So by third year for my undergraduate study, my choice was pretty much clear. So when I was third year undergrad, I entered this Ginzburg theory group. So I had to take, on my third year, I had to take additional exam in theoretical physics, in classical field theory, and I entered Ginzburg theory group, from which I graduated. Graduated meaning with masters, because this institute, so when you enter, you will stay for 6 years. I mean, used to be, right now they changed, 6 years without any bachelor, because I mean, like there is no point to be a bachelor in physics, because I mean they were training not teachers but really scientists. I mean, so I mean, like what would you do with bachelor in physics if you know? I mean, you cannot become a scientist. So the lowest degree was master's degree. So I graduated from that place, and then that's the next steps. I mean, so I did PhD at the University of Alabama. Then I did my postdoc at Syracuse University. Then while I was waiting, so by that time I was kind of tired of the United States. So I got offer from the São Paulo University of São Paulo for the next postdoc. And while waiting for some, actually it took a very long time, like more than half a year. So while waiting for all the bureaucracy to be resolved, I was visiting professor at Georgia Southern University. And so that was at the moment, this is where I stand. Okay, so more or less that's the path, right? I mean, so, but what kind of challenges? I mean, a lot, of course. I mean, so, but the point is that that's exactly the point. I never considered them to be challenges in the sense that, like why? Like sometimes I hear during my classes here, like, oh, but like why is this so complicated? Like can you give us like classical mechanics on a simpler level? The answer is no, because that's the level of classical mechanics. I mean, so the point is that I had fun. So in some sense, that it was very difficult, very challenging, but that's what I wanted. Okay, so so in some sense, that's why. Once again, as I used to say, so science, I mean physics and mathematics, they always, as you saw, like since like first grade more or less, they have been my hobbies. And now, for some reason, I'm even getting some money for my hobby. So typically you pay for your hobby, right? I mean, so if you collect stamps or coins, but I'm having a hobby for which I'm being paid. So that should be your attitude. So you cannot consider being a scientist as a job, because the moment you start considering this as a job, you're doomed like to be bored the rest of your life, because typically job is something that you have to do. This is something that I do because I want to. Okay, so if you feel like that, then you definitely belong to physics. I mean, so it's much more important to feel like that than to be some very smart person. Okay, so because I mean, if you really enjoying that, you have much better chances to succeed, even with some not so good initial conditions, like not so good school, for example, and stuff, because it's fun for you. So I mean that you do this because you enjoy. And if some smart person will do it because he or she has to do it, I mean, almost no chance that they will actually succeed. They will be doing good job, teaching, maybe even once in a while producing papers. But I mean, because they don't enjoy, like, why? Okay, so that's the point. I mean, yes, I mean, challenges as a researcher. I mean, every problem is a challenge, but once again, that's the challenge which you choose, like, to be your challenge. Because strictly speaking, after you became a professor, nobody forces you, right? I mean, so, but because you really feel like you want to know more, you one more advice, not directly related to that. So this is advice slightly for the future when you already like become, because I mean this is a dangerous advice before you found job. But once you're more or less settled, I mean, you should never try to chase some fancy problems. Do problems which you really care about. I mean, meaning that even if the rest of the world does not give like nothing, anything about that problem, but for some reason this problem is interesting for you, forget about the rest of the world. Solve that problem, because you will be really enjoying when you will find the answer, because that was your problem, and you answered that question which you asked. Of course, I mean, the point is that when you have like collaboration, interaction with the rest of the scientific community, of course, scientific community will have some effect on what you think is interesting. So if you like completely isolated, of course, the choice of your choice of problems will be very specific, because you will not like have interaction. You will not know much what is going on. I mean, so that's why it's very important to interact. I mean, but I mean, if after all the interaction, all the like discussions and all the stuff, you still come up with some problem, and some other people say that, no, I don't know, it's not interesting problem, don't listen, solve that problem. Okay, so that's
all right.
The next question is from Lorena, and in your opinion, what are the good and bad habits you can identify in Brazilian physics students? What are the main differences between physics Russian students and Brazilian?
So before the interview started, I said that I will try not to enter dangerous discussions. So this is a very dangerous question. I mean, no, of course. So first of all, I cannot judge the situation with Russian students right now. I mean, because unfortunately, due to mostly like political reasons and all that stuff, I had to leave Russia pretty long ago. So let's say for the past 20 years, I enjoy Russia as a tourist, essentially. Okay, so I mean that I have not much of an idea like what is the situation with students right now. From what I hear, it's the situation is still more or less okay, but not as great as was during Soviet Union. Because I mean they had to change the way the university works and all this stuff. I mean, so I would say that the main difference, I cannot say like good and bad habits, but I would say that the main difference, which I can see on the positive side for Russian students and on somewhat negative side for Brazilian students. And this is not the problem of students or even the university or even universities. The problem is with the school, with the previous step. So the point is that when students arrive to university, when they enter university, they're already like 18-year-old or something like that. I mean, so meaning that they're pretty much grown-up people. I mean, they might be like still stupid, like thinking about some going mostly to bar and not to university, but otherwise they're grown up. So meaning that they're already formed as people, and unfortunately, the school does not prepare them for the independent work. Even the smart ones, they don't know how to study. Meaning that a lot of students, they really think that to study is equivalent is to go to the university, while the study actually only begins after you come home from the university. I mean, the major part of study should be done on your own. University should give more or less the level on which you should know the stuff. So you cannot study during the lecture. During the lecture, you can like really like to understand, okay, so I have to know this material to this level at least. Then you go back home and you study and you work and you work and you work. It does not mean that you don't go to bar or to some concert. I mean, but I mean, you really should learn how to find that balance. So I would say that Russian students, I mean, let's say Soviet students, they were better prepared for that, because I mean, Russian school was already requiring a lot of work essentially, and it was really built in such a way that it would prepare you to understand what does it mean to study. So, but then I mean, of course, it has some positive side for Brazilian students. I mean, they are much more easygoing, relax. So meaning that because I mean, if you just really think that okay, so I have to work, I have to study, and also it's very easy to be stressed a lot. So, and that could be, of course, I mean, very dangerous, even from medical point of view. So Brazilian students, I would say that they are running much lower risks to encounter that problem, because I mean, once again, I mean, so you are not that much concerned that something, for example, is not. I mean, you cannot learn something. Okay, so if you're hard working, you just okay. So you put it behind, you keep on working. So it does not kill you immediately. So for me, it's like that's back to the previous question. So I'm really annoyed. I mean, really, if I don't understand something after some quite short period of time. So meaning that that is very like distresses me a lot. I really have to understand whatever question I ask. I mean, so I mean, I don't ask all the questions. For example, I don't care something happen somewhere. So if I don't care, I'm not preoccupied that I don't know answer to that. But if I want to know something and I don't understand something, that is very difficult for me. And that does not help all the time. Okay, so that's the point, because sometimes it's very useful to have that quality to put it aside, relax, do something else, and come back maybe later to some greater success or greater chances to answer that question. Okay, but because we're in Brazil, so my advice would be the following: try to work harder, really by forcing. First steps will be really painful. You will have to force yourself, really, like writing down the schedule that today I have to study like 6 hours of independent study. I mean, so I'm not kidding, really. I mean, so like 6 hours. So when in my university, I already told to many of my students, I mean, so first 2 semesters, so first year of undergraduate study, only in classes, the first semester, I had 42 credits, so 42 hours per week. So by constitution, it's illegal, because by constitution, you can work only 40 hours. But that's only 42 hours of classes with a huge amount of homework, so which would require almost the same number of hours. So essentially, first year, we were talking like classes, work, or study at home, sleep. And occasionally, of course, I mean, you go to some just fun with friends, but that's really like occasionally. So of course, I mean, because here the situation is different. That's why you have to force yourself to work. I mean, really, like say that, okay, so 2 hours of quantum field theory or whatever the analysis, like each day, whatever.
So just a brief commentary.
Was it a question? Was it a question? No.
No, that was not.
Comment, no? Okay.
So just a brief commentary. You probably know about this already, but when Feynman visited Brazil, he said he saw a lot of young people learning physics, but they had no understanding of the physical meaning of what they were learning. Do you notice this at all?
No, so that would be another question, but that will take me even closer to dangerous ground, right? I mean, so the point is the following: that serious problem which I encountered, this distorted vision or understanding what is science, not just physics, but what is science. Actually, we discussed that with Alison just yesterday. So more and more I see that students really like see the science on the level of some popular books, really like kind of like closer and closer to some science fiction. So the best characterization of my point is the following. One of the questions which I had quite some time ago here. So we were solving some problems, a lot of integrals and all this stuff. And some guy really, like, honestly, he believed in his question. I mean, asked him, so, no, but why are we doing all of this? I mean, this has nothing to do with coming up with some new breakthrough theories. So that was his word, like breakthrough theories. I mean, so I entered physics really to create some completely new great theories. I mean, so when I told him that before you do that, you learn how to integrate, he was completely unsatisfied by my answer, because he honestly believed that you can really succeed essentially just by having great ideas.
That's a series of steps, you know.
Right. I mean, that is unfortunately that happens quite often. So for that, I think it's very important that our courses are maintained on some high level. Meaning high by high, I mean that you cannot go lower than some level just because somebody does not understand or something like that. I mean, so we actually not helping people. We actually causing very serious harm by going lower and lower and lower, because I mean, people would think that, okay, so I'm following, so I'm pretty cool. But after that, he graduates and tries to enter the actual science. And that will be very serious stress when the person will see that the actual level of science has nothing to do with the level of something that he learned, for example. So the main problem of the university, I would say, is to prepare, not just even to give knowledge, some knowledge. Knowledge should be acquired by a student because he's interested, but really to prepare the student to face his future in science, in such a way that he will be not scared to ask questions, in such a way that he will not be scared really to admit that, okay, so I don't understand that. I mean, so it's okay not understand it, but the consequence of that should not be like that everybody will descend to your level and all stuff. No, I mean, the consequence is that you don't understand, you try to understand. So that's the main function of the university. I mean, when I say university, I mean that I'm really talking about the university training physicists. Of course, I mean, that does not apply entirely, for example, to this licenciatura part, because the purpose is completely different. Right? You cannot, and the point is that it does not mean that this is better, this is worse. No. But the point is that depending on purpose, I mean, so if you decided to be a physicist, you cannot be a physicist who knows quantum mechanics on that level. I mean, quantum mechanics is just one level. It's quantum mechanics. I mean, systems in quantum mechanics can have many levels, but quantum mechanics is really it's one level. It's ground state. I mean, quantum mechanics.
Fair enough.
Okay.
So we have another question by Lorena now.
Alison, I think there is a question here that's in the same line, so I'm
just going to skip it.
Then we can do it right now. It's from Leander. He says, Professor, I had the privilege of being part of perhaps your first lectures in UnB back in 2009 in Quantum Mechanics 1. Was there a significant change from those years and today in your field and classes?
That's even more dangerous, bro.
Yeah, so, I think that's the less dangerous question we'll have.
So, hi, Leander. So, I would say that for me, it's very difficult to compare in the following sense. So, okay, so I will be politically correct, but honest, but not completely honest. Okay, so and then you decide. I mean, so what do I mean by that? I mean, so why I'm saying that? Because 2009, it's exactly my first year when I became a professor here. So I mean that I came to Brazil in 2007. But for 2 years, I was just really just researcher. Just a researcher means that I did not do any teaching, nothing. So 2009, I just entered, and for me, the whole thing was completely new, because as I told you, the difference not just really in level of preparation, in the level of preparation of students and all this stuff, but really on every level. It's very different from what I used to think about universities. It does not matter whether it's different, better, different, or worse, and all this stuff. I mean, it's just different. So for me, actually, I would say was much more difficult than for students because I really had to do a lot of adjustments. I mean, I don't envy students. because I mean, poor Leandro, because I mean, my Portuguese was really zero at that point. I mean, zero meaning that essentially after 2 years, I could manage just to say that no falo português. Okay, it worked pretty well actually. So because I mean, Brazilians are very nice people. So after that phrase, everybody would start trying to help me and all this stuff. I mean, so I mean that I kept on using that phrase even after I started speaking Portuguese a little bit. I would still say that I don't speak Portuguese, so people would just let me go in front of the line and all this stuff. So in the bank, in the bank, it worked like a charm. I mean, so you come to the bank, it's some huge line, and then you start playing some stupid foreigner who does not know what is happening. Manager would come out, take you by hand, and just take inside, and that's it. I mean, and you just look back at the whole line and just like, losers. So anyway, that's why it's very difficult for me to compare the levels, because the points right now, I really know what to expect. So right now, I don't like listen to my feelings and all this stuff. I'm trying at least a little bit to feel students and all this stuff, right? I mean, so to communicate, to do some adjustments to their level, not very much. I mean, but that I announced at the very beginning each class that I will not really drop the level. I mean, so but still, of course, I mean some compromises and all this stuff, because right now my level of the communication allows to do that. I mean, so that first year, I was, as I said, scared much more probably than students. I mean, so the point is that typically I would use some person in the class, like to translate the questions of other people who would ask me something in Portuguese. So the other person who would speak English would translate that question. Then I would think and try to answer in some primitive Portuguese and all this stuff. So mostly my classes were like, I wasn't talking too much. Mostly I was writing on the blackboard. I mean, so, and just like facing once in a while, like looking back, like, are they still alive? So hoping that they are not. So because if they're dead, then I should stop and that's it. I mean, so. But that was fun. I mean, so of course, I mean, on a serious note, there is a change in the level of students. I cannot say that if this change due to some structural changes in the country, or it's some local change due to the university itself and all this stuff. I mean, so, but I do feel some changes. I don't know, maybe. No, I cannot say. But if I would have to compare 2009 and 2020, they're different turmos. Okay.
All right.
By motivation, mostly by motivation, I would say. Different motivations. I will not enter discussing different in what sense, but they are different.
Okay. All right. So let's move on now to the next question. And I'm actually going to combine two questions that we received here. You already gave some advice for people in the undergraduate level, but now people want to know what would be your advice for people at high school level, so young physicists or people who just have interest in physics, but are still at a very early age.
So, because my advice for undergraduate level was like, it's not too late to quit physics. For the school kids, I mean, don't enter. No, so seriously, it's like that. I mean, essentially the advice would be the same, right? I mean, so because probably the program in school in sciences is not too great I would advise already while you in school. I had actually this experience here in Brazil, in Brasília. So some school kid, he still was like 2 years till he would graduate from the school. He came to my office and started talking to me, like asking what he should read, like to get better understanding what is physics, what is mathematics, and all this stuff. I mean, so I would say the best advice would be look for someone who can help you. If this is your school teacher, great, you're lucky. Talk to him and say that I'm really interested in science, in physics, in mathematics, and all the stuff. I mean, so what would you advise me to read, to really get better idea what is that? I mean, so the first step is to get the idea what is science, and this is the most dangerous step, as I already explained, because I mean, if you get this idea from a wrong person, you can have a distorted idea that science is really like direct path to a Nobel Prize. I mean, through the steps of great discoveries. I mean, so doing science, first of all, is a hard work, but not in the sense of a job, but really of the sense of hard working. I mean. So you really already being at school, you should kind of appreciate that. I mean, okay, so but once again, the best what you could do in this situation, to look for a person who can give you some advices what to read. So in my case, it was slightly easier. I mean, first of all, because I went to the specialized school. Second of all, because we had a very good selection of literature, meaning that it was called popular literature, but in Soviet Union, popular literature for kids. But just to give you understanding, kids meaning that even not for the high school, but like for 6th, 8th grade, I mean, 9th grade. So the point is that, for example, that particular book which I'm talking about, it had explicitly written Lorentz transformation. So I mean that already in the popular literature, they considered Lorentz transformation a non-relativistic limit. So meaning that I had to expand this gamma factor 1 over square root 1 minus v squared over c squared to understand why that gives me usual kinetic energy and all this stuff. That was considered as a popular literature for kids. So while in school, you would like to have something like that. I mean, that you would understand that science is really a challenge which you choose to be your life. Okay, so the worst thing which could happen is that you will really think that science is fun, but without the hard work. Okay, so once again, advice is very simple. Try to find someone who will mentor you, and probably that someone should not be me, because my motto, once again, don't enter physics. Okay. So and of course in the high school, the point is that first of all, you should make sure that at least the high school material in physics and math, because it's pretty low level of the material, that you don't have problem with that level. So that should be like a first check. I mean, so that you really very like free talking on that level of physics and mathematics. I mean, so because I mean that is like zero level. Okay, so if you feel that that level of math is not enough, or physics is not enough for you, that's the first indication that might be you need the next level. Then look for a mentor. Okay.
Thank you for the answer, Professor. We are entering in our second hour of live, so I would like to ask you, there are a lot of questions yet, and would you like for us to make a 5-minute pause? Or can we...
It's up to you. I mean I'm fine. So
you're fine. Okay.
Yeah, I'm still having something.
Okay, so we are going to...
It's already cold. It's already cold, but I'm still pretending to drink it.
Okay. Well, if you want us to take a break, just tell.
No, that's okay.
Stop for a little. Lorena has another question here. What are the ways of building a more collaborative and healthy environment to stimulate the rise of new discoveries in our Physics Institute?
A painful question, right? I mean,
painful corner.
Actually, that's not a joke. I mean, so the point is that.
Yeah, I know. I mean it seriously.
Right.
If you want, we can just skip this question.
No. So the point is the following: that the atmosphere is playing a very, very great role. So meaning that the short answer is the following: that Institute of Physics should feel as an Institute of Physics, really as the group of physics, not necessarily like all should be friends and all this stuff. I mean, that never happens. Like we have like 70, 80 professors and all this stuff. I mean, so you cannot be friends with everybody. But it should really feel like a home for science. And if it's a home, of course you have some place for coffee. You have some place where you can sit, discuss some common room for professors and all this stuff. So every place, so you've seen the list, the places where I worked, studied and all this stuff. Every place has like that. I mean, so I mean that where professors really, I mean, students should have also like that. But I would say that students have more. I mean, students will disagree, but I insist that students have more than professors. Not because I mean we cannot do that, because in some sense it seems we don't want to do that. So students have this student room, right? I mean, at least some point where you can intersect as a community. So I would say that healthy environment should have some point of attraction. Attraction not in the sense of amusement park, but the point where people will feel like belonging really to some organism. Okay, not just working at that place, but really. So, like we used to have in some other places, every Friday, the whole group would go have some lunch. Like some other places, at 3 o'clock, there will be some gathering where people would have some coffee. A lot of people would come with their own coffee or tea. They just discuss stuff. Okay, so once again, I mean, it should be something such that people will not feel like belonging to separate groups. So there are separate groups inside the institute, that's for sure. But they should feel really on the top of that. They should feel belonging to the institute.
True.
But the Institute of Physics, okay, so which means that, I mean, every organization has a lot of problems. When any organization involving people has a lot of problems. physics should be above all of that. It should come in the first place, in the ahead of any money, any whatever. I mean, it should be physics, and every other question, every other problem should be subordinated to physics. So if we succeed that, we will have an Institute of Physics.
Let's hope for that. All right, so the next question is by Gabriel. He's asking, what are your thoughts on the teaching of mathematical physics in the near future, given the increasing sophistication of both mathematics and physics?
So what we teach right now is a mathematical physics. So mostly it's in 19th century and a little bit of beginning of the 20th century, right? I mean, so it's not actually mathematical physics which we're talking today about. I mean, during this interview, right? I mean, so I mean that mathematical physics as an area of as a research area. So what mathematical physics which we teach right now is like ground level 0 mathematical physics. So it's more like applied mathematics, like necessary tools from mathematics to become somebody who can at least solve some equations and all this stuff. I mean, okay, so that is mathematical physics. So that's why sometimes, for example, this part, mathematical physics A, should be called actually like equations of mathematical physics. So mostly this is it is what I'm teaching. Mostly this is really a study of methods of equations in partial derivatives applied to physical problems. So that was like mathematical physics of 19th century, once again, when it was a research area. So what I'm thinking, how it should be done. So of course it should be done. I mean, that mathematical physics, which I just said. I mean, this mathematical physics A, B. Of course, it should be taught. I mean, so it's a 0 level, so you cannot skip that. What we are lacking more specialized courses. So the only way, I would say, in view of this increasing sophistication, is really to give more focused specialized courses. I mean, it should be a course in geometry, not topics, but really regular course. In geometry, like there are books like geometrical methods in mathematical physics, right? I mean, or geometrical methods in physics. So that should be a course. It should be a course on functional analysis from the point of view of physics, where it's applied and all this stuff. I mean, so why I'm saying that those courses should be specialized courses, because by the time when students should be able to take those courses, they should be already able to judge whether they need those courses. So this level 0 mathematical physics should be, of course, taken by everybody, independently of what is your future area and all this stuff. But after that, I mean, you should be able really to tell whether you want to continue in that direction, and then you should be able to have a list of the courses from which you can choose. Okay, so I want to take this, for example, course. Then you go to a professor, and professor says that, okay, so do you know that? You say, no, I don't know. So then better take that course. I mean, so it's not necessarily should be in the form of prerequisites. Because, I mean, the guy maybe already, or the girl, they already maybe learned complex analysis of many variables just on his own. And then I can just talk to him, and in like 10 minutes, I can figure out that, okay, so he does not have that prerequisite formally, but clearly he will be able to follow the course. Okay, so this institute of prerequisites for specialized courses is not necessary. So, but what is necessary? Yeah, because I mean, of course, you cannot expect that the specialized courses will be like crowded, like 20 people. So typically, you're talking about like really 5 people plus minus something. I mean, so of course, I mean, I can talk to those 5 people to figure out and to give some advice whether he should take. So and just ask why is he taking that? What is his expectations? I mean, maybe once again he's taking because it just sounds cool, but he really does not need it. I mean, of course, I mean I cannot forbid, but I can advise like don't waste your time. Okay, so I think the scheme of more diverse specialized courses, and once again not topics, should solve the problem quite easily.
All right.
Thank you. Well, the next question is from David, and he says, do you sense a pattern towards abstraction in the math used in physics as the physical phenomenon gets more complicated? Something like going from numbers to vectors, then tensors and functions to operators, and etc.
So the simple answer, I think that it goes towards the simplification. I really think that operators are much easier than tensors and all this stuff. I mean, but I understand the question, of course. I mean, the point is that it really depends on your perception. What does it mean complicated, more complicated, and all this stuff. I mean, so in some sense, as I said, the apparatus becomes simpler in the sense that it becomes typically more general. So in some sense, in many senses, quantum mechanics is simpler than classical mechanics because it's more the foundations and the basic equation just there. I mean, and it's very simple to grasp after you understand what is that. I mean, so the general idea is that general formulation or general theory typically is simpler than the specific concrete cases. I mean, so for example, if you like just start solving some problem in quantum mechanics, even if you try just like to derive from Newton's equation 3 Kepler's laws, it already does not look very simple. While Newton's law, the second law or 3 Newton's laws, are quite simple, right? I mean, so because they're general. So once you try to specify for some concrete problem, it becomes more complicated. So that's one thing that I think it's really not correct to say that mathematics becomes more and more complicated. It becomes more and more general, I would say, in such a way that, of course, I mean, to generalize, you are stepping on steps of all the previous developments, like to construct function analysis. Of course, you use all what you know from usual analysis, from other areas. But the point is, once you get to the point of generalization, then you see the beauty of this general construction, and you actually obtain new point of view on something in the previous steps. I mean, so you understand, so that was actually from here. That's why it's very natural. So in this the previous level, some things were disconnected. Only after being like united in some more abstract theory, they might find the explanation on stuff. So for sure, like, typically,
I feel like this is related to the next question. So it's another question by David, and he says,
right.
Banach said that a good mathematician sees analogies between theorems, and the ultimate mathematician sees analogies between analogies. Do you think something like that holds in physical theories? Sort of seeing the greater picture and seeing all the...
in some sense, You might say that, but in some, I would say the closest to that would be what I said, that the best chances to become a great physicist for you is really to see the physics as a science, not just like a condensed matter, that. I mean, so if you like really think within one area, like within condensed matter, you can have, and if you're strong physicist, you can have very strong results there. But unless you will start seeing analogies between condensed matter and quantum field theory, you have not that great chances actually to create something really impressive. Okay, so I would say that here probably you need to say something like that you have to see the connection, the first level, to see the connection, the relation between some phenomena within some area, and the second level to see the relations between areas. So relations not necessarily like the same physics. No, physics completely different, but relations that you really start feeling, oh, physics completely different, but it looks very much somehow similar intuitively, like using relativistic Dirac equation in the description of the physics of some condensed matter, problems, right? I mean, so I mean, clearly condensed matter problem, non-relativistic ones. I mean, like in graphene, the graphene, you exactly use the best. One of the best approaches to describe the spectrum is using relativistic Dirac equation, because I mean people see, so it does look like the spectrum of the relativistic Dirac equation. Let's try and applying. All of a sudden, you have better handle how to explain some effects, explain on phenomenological level, really to calculate something and explain some numbers. Though I mean, raised relativistic Dirac equation and raised graphene, completely different physics. Okay, so I would say that in physics you should not work like analogies or between analogies, but really like correlations between phenomena within one area and correlation between areas. Okay.
Very good.
We arrived at our last question right now. It's from Yelena, and she asks, what do you think is the most underappreciated discovery in mathematical physics?
So, I mean, I don't know, it's probably not a secret. I mean, so that's my daughter from the States. I mean, okay, so I will talk to her later, but I mean, so the question is actually a very unexpected question. So let me think. I mean, she's doing genetics, so she's allowed to ask questions, whatever, and those are the most difficult ones, because I mean, you never expect this kind of question, because I mean, she just, okay, so for her it's natural, because she does not do physics. I mean, so because my point is that all the previous questions I could really expect, because I mean, that's asked by people who know physics and all this stuff. I mean, underappreciated discovery in mathematical physics, I would say, I mean, I don't know whether it's the most underappreciated or not. I mean, but the point is that I think that people did not appreciate much and did not pay much attention to the development which happened in 60s and which started with Weitman, Haag, Kassler, and some other people, which goes by the name of what's the name? Axiomatic quantum field theory, and became later algebraic quantum field theory. So, meaning the following, that that was an attempt, ongoing attempt to address the questions of quantum field theory or of local quantum physics, really as they've been addressed in some sense in mechanics, quantum mechanics, like you do as mathematicians. You define the list of rules, which you call axioms, which are based on more or less reasonable physical observations. And then you try to derive as many possible physical consequences from them. Essentially, you try to develop the physical theory out of that. Because, the level of complexity, essentially, the journal, the Communications of Mathematical Physics, remember the two journals, Journal of Mathematical Physics and Communications of Mathematical Physics was created by Haag and Jost to publish paper on that subject. They created the journal, really to address those questions. But because the level of complexity was so high as to be appreciated by other physicists, that it remained area, like devoted area, devoted to some group of devoted people, of the followers who can follow. Okay, so the point is that, but I do think that is one of the ways. Slightly it started being appreciated. But that might be the path to new physics. Really, the analysis of the defining rules of the game. Which rules are really fundamental? Which rules could be bent? Which rules could be really thrown away? And what will change in the physics? So by really deep understanding why we have physical theory like that. So in which assumptions it's rooted, on what assumptions is based, could help us understand what is the next step. So I would say underappreciation of this activity has two reasons or two sources. First source, of course, technical complexity. It's really very heavy mathematically, really very heavy. Second of all, I would say it appeared in not very lucky time, 60s. 60s was time, and then 70s, of great success of the conventional quantum field theory. Really success in the physical sense. People could calculate stuff. 72, 73, the discovery of asymptotic freedom, which allowed to start working with quantum chromodynamics independent of the fact that confinement could not be explained. So actual successes, which show that in some sense, this recipe, which is attributed to Feynman, but wasn't said by Feynman, but more or less, you could see Feynman saying that, like, shut up and calculate. So shut up meaning that don't bother for a moment why it's working. If it's working, and it's working just not fine, but perfectly to many orders degree of precision, calculate. And I think that somehow like side-blinded the community a little bit, and community got too much involved into calculation and not too much involved into really trying to understand why it's working. Okay, so that would be my answer to that tricky question. Okay, a trick question actually.
I could have sworn you were going to say that it was the discovery of the requirement of twisted point covariance symmetry in non-commutative field theories.
No,
Okay.
no.
So,
I mean, I worked on that for some time and enjoyed working. But that is what I called like phenomenology in mathematical physics. So of course, I mean, there is not much of phenomenology, but the point is that it's not a fundamental theory, but it's some attempt. So the point is the following: when you don't have a fundamental theory, and actually you don't have a clear idea in which direction you will find a fundamental theory, any attempt should be appreciated. So you just try something. You try that. You try that. You try that. Of course, I mean, all the time while trying, you are motivated by something, but essentially you're just trying. So okay, so let us, like mathematician, let us add that structure. So what will happen? So in some sense, this non-commutativity, of course, I mean, has a very strong motivation, meaning that one way or another, if you do believe in quantum gravity in one form or another form, then some modification of the notion of the smooth manifold as our space-time should be modified. And you can even argue that this modification, at least for some regime, will look like some kind of non-commutative geometry. And then you start playing with that to the extent which you can play. So it's a nice game. But I mean, after some time, you got tired. Okay, so in some sense, one of the papers which I'm like proud about is not that much cited papers, but it was the paper by which I closed the topic for myself. That was my last paper in that area. It was like 8 years ago. Exactly. I just tried to see some anomalies in that description. I liked very much paper, but that's it. I mean, so it was my like fat point in my participation in that. Meaning that if it ever comes back in one form or another, I might re-enter. I might like revive it even myself. But I mean, at the moment, I feel like doing some other stuff. So that's actually another reason why you should learn a lot of stuff, even though maybe it's not of immediate concern or application for you at the current point of your career. Because as I told Alison some time ago, it gives you freedom. So you're tired of something, you just, okay, so I will do that, I mean, because it seems like fun. But if you just really picked some very narrow path, not even area, right? I mean, so a narrow path is when area degenerates in a line. So it's become very difficult actually in the future to be flexible in the choice of your scientific interests. So essentially, you'll be stuck for the rest of your life doing non-commutative geometry in some sense. It will be fun for 10 years. Maybe it will be fun 20 years, but then you will want to do something else. I mean, non-commutative geometry in the very narrow sense, once again. And you would like to try something else, but you cannot. Because, I mean, you don't know much other stuff outside of the area or this narrow path, and you're kind of too old. I mean, so it's not a joke. I mean, that with time, when your age is, unfortunately, due to the entropic considerations, your age goes only one direction, right? The time of flying, unfortunately, like only in one direction progresses. It's much more difficult to learn new stuff. Okay, so while you're young, that's the main advice. While you're still young and your brain is fresh, adventurous, and all this stuff, learn as much as possible.
Excellent.
And to learn it effectively, find someone who will help you. That would be the like final advice.
Well, that was an excellent way to end it. That was our last question. I just want to thank you again, Professor, for accepting our invitation. I want to thank everyone who participated as well. People are also thanking you on the chat.
Okay, thank you for inviting me. It was fun. I told I told at the beginning that I'm very selfish person, so it should be fun. First of all, it should be fun for me. So if it's fun for someone else, great. I mean, so if not, I mean, so not my problem. I mean, so it was fun. It was fun for me for sure. I mean, so
I think we succeeded. All right.
Thanks.
See you, everyone.
Okay. See you guys. See you,
Professor.
Next semester. Someone next week. Okay. See you guys. See you.
See you.